Great, let's get started. So we didn't finish SVM, so I'm going to first finish those. And I'm going to just kind of reuse a lot of the slides very, very quickly just to refresh you how we got to where we are, so you're not disoriented. So the idea was we're going to design a new kind of classifier where we define this thing called the margin, which is sort of the buffer region of where no points lie, and to be correctly classified, you need to lie on the correct side of the margin. And we first did this with this sort of hard formulation where there was no allowance for errors, and we said that we could write the margin as 1 over the magnitude of the normal to the separating hyperplane, right? And then we had these constraints that that this dot product had to be greater than 1. And from there, we got this quadratic program, and we said you could make a call to some quadratic program solver, which was beyond the scope of this course. And then we did this sort of brief refresher, or for some of you, maybe introduction to the Lagrangian, the dual and the primal formulations, and how that leads to a different quadratic program that's amenable to being kernelized, and that has a different time complexity dependent on the dimensions and the number of points. So and I'm going to refresh you very quickly because we're going to use this to go from the primal to the dual, which I skipped over last time. For the hardy SVM, you can use these techniques to go from one to the other, and I'll show you how to do that with the soft SVM. So that's what we're going to do today. So the idea was you have these inequality constraints, equality constraints, and you go through a series of steps to change what was a constrained optimization. You have this function with these constraints to something that actually was unconstrained, mostly, except for the lambdas, which arise from the inequality constraints. And now the trick is that you have to do, inside of your minimization, you now have to do a maximization over these dual variables for this to be the same optimization problem. And if you do that, then if you're able to get a solution to that, this is called the primal solution. And these here are the augmented variables or the dual variables, right? And then what we said is that if you reverse the order of the min and the max, which would be convenient for us to do things because it's easier often to work in this way, then you get another solution, which is the dual solution. And in some cases, these are equal, and when they're not equal, there's a duality gap. And in this course, we're just going to look at it for the SVM. In that case, they are equal, and so we don't need to worry about that. And so once we've set it up that way, then we're going to, in particular in this lecture, but in general, you may want to make use of these KKT conditions, which basically say that if you have strong duality, then at an optimum, all of these conditions are satisfied. And so what that means is when you're looking for an optimum, you can use these to manipulate the math into simpler forms. And that's what we're going to do today in order to go from the primal Lagrangian to the dual. And so I quickly went over some of the intuition. The one that is probably most obvious to you is this last one here, which is the gradient of this Lagrangian has to be 0. Right, and then there is this point that we've said throughout the course, which is although you didn't see it with respect to this kind of duality before, but you saw it with kernel ridge regression, which is in the sort of original formulation, it was good when n was much bigger than the number of dimensions. But if you had it the other way around, or you wanted to use a kernel to lift your feature space, then you wanted to use it in this other way with a kernel. And here that emerges very naturally when you use the dual formulation of the Lagrangian. So from there I said, okay, now let's go to the real SVM that you can actually use in practice, which was the soft margin SVM, where we allow for these errors here. And in the soft margin SVM, we have these slack variables, or these error variables, and now we allow slack in the decision boundary, right? Instead of this having to be strictly greater than or equal to 1, we're allowed this sort of slop where we can take off epsilon, and so that's how you account for these errors. And correspondingly, we needed to augment the function up here, not to just maximize the margin, but also to take a hit if we incurred any costs. Otherwise, we'd just get nonsense out. And again, this also could be, it's just a classic quadratic program. Okay, right, and then the idea was, how do we go from here to here? So I just showed you this result for the hard margin, and now let's actually walk through it for the soft margin so you can get an idea of how to do that. That's where we were. Any questions on the recap? Okay, you can see my laser pointer. There's no notation problems yet. All right. Okay, so basically, this is up in the top right here. This is where we said we had as the soft margin SVM. We say minimize the reciprocal size of the margin and add this cost expression in, subject to this new slacky decision, if you will. And also those slack variables have to be greater than or equal to 0, or it doesn't make sense. And so we can go through, I won't go through step by step as I did in the little tutorial, but we can take, basically these are all inequality constraints. So there's two inequality constraints for each point, which means that I should have 2 times the number of points dual variables introduced. And so I have 2 dual variables, kinds of dual variables here. One arises here is the lambda I get for every point, and the other one is the beta I, right? And so this beta I obviously corresponds to the second inequality constraints, and this alpha I here is multiplied over this whole term, which arises from the first inequality constraint, and then this is simply the function. And then these dual variables are also, it's not written here, subject to being positive again. So this is just sort of turning the crank of going from here and turning it into the primal, into the Lagrangian right now. Okay, so right now that's just almost formulaic, although hopefully you understand the principles behind that, or you have time to read about that. And so, right, so now I can rearrange the terms. Right, so this, like, for example, the C, the alpha, and the beta are all getting collected together that multiply on the epsilon, right? So there's one here, there's an alpha here, there's a beta here, those are all going in here, and basically I'm just collecting terms from this line to the next line. And then once I do that, now I can say the dual Lagrangian is to maximize over the dual variables. Right, because I've switched the order of G, where G, right, in the dual I switched the max and the min, so this is now the dual, the max, and G now itself has a minimization in it, so it's just getting written in here, and so I want to find the max of this function, which itself is a minimization over the primal variables. So this is just, I mean, this is just notational, I've just copied and pasted this down here. And just emphasizing that you're doing a max of a function, that inside of it has a min. And the outer one is the dual variables, which are just these sort of things you've added for convenience. And the inner one, those are the things you actually care about, right? We're trying to find W and we're trying to find beta. But in the end, we're going to do those by actually getting a value for alpha and then back computing it. So basically, what we're going to do now is, because there's no duality gap, we're going to work with this dual formulation and try to get somewhere, and in fact, try to get a solution for the alphas. That's our goal right now, is to go from this dual to get the alphas. And then once we get the alphas, I'll show you how you get W and B out of it. Any questions? Great. Right, so first what we're going to do is we're going to use, remember those KKT conditions, there's a bunch of them, and I said the most obvious one you've probably seen in your Math 53 course is that the gradients of each of those terms has to basically equal 0. And so we can take the gradient of each with respect to each of these in turn. So first of that Lagrangian, which I've written down here with respect to W, I basically just get this here, right, because W only appears here. In this part, so and then I just trivially get this term out here, and that's set equal to 0. From there, I can just see that W is actually the weighted combination of the training points. And so that already tells you that if I can somehow figure out a solution to the alphas, I'm going to be able to read off W from here, right? So that's like a look ahead. So right now, we don't know alpha, so we don't know W, we just know it's this particular function of W, and then it's a weighted combination of the points weighted by their class, -1 and +1. Okay, the next one we can do is, that was the W, now we're going to move on to the beta. So I'm going to take the derivative to B, and B only appears here, right? It's just in this one spot here, so I just get the alpha YIB coming out, and it's the B comes out because I take the gradient. This is super simple. As I have some kind of intuition, tells us that basically the alpha i's across classes have to sum up to the same thing, which doesn't necessarily mean a lot right now, but kind of an interesting point. Okay, the third one is going to be the gradient with respect to these auxiliary, or these are still the primal variables, these are the errors, because these didn't arise from the Lagrangian formulation, they were just this weird thing I put in my original objective function, and that guy, I've collected all the terms down here, and so when I take the derivative, I get basically for each, right, it decouples by I, and so each of the i's gets a term like this, and this just tells me that alpha lies between 0 and it's capped by C. And C is the penalty term that we choose with cross-validation, right, on how much we're going to penalize the sum of the slack variables. Okay, so that's sort of what we're going to do is we're going to keep using more of the KKT conditions to make progress on finding a solution for alpha. And then again, we're going to back out of it. So far, we basically obtained these three expressions. W is a function of alpha, these alpha yi's have to sum to 0, and each alpha lies between 0 and C. Okay, so we're not at a solution yet. So what else can we do? We can take those results. So each of those three results, we can take, well, some of them as convenient, and plug them in. And so in particular, we said that these have to all be equal to 0. That was which one was that, alpha I? That's the second one here, right? I'm just making use of this, and I'm plugging it in, so I'm going to cross this term out. And then I'm also going to do, there was this one here also said that these three have to be equal to 0. Yeah, this minus that, right? So also these terms fall out, which leaves me just with these terms. Okay, so by using the stationarity conditions, I could solve for some of my primal variables in terms of the dual variables. Then I plugged that in and I got rid of them, right? Some of them. I got rid of, what did I get rid of? I got rid of beta, and I got rid of the slack variables. They're gone. So that's nice. More variables we can get rid of, the easier it's going to be, because as I said, ultimately we're trying to actually get something that's just a function of the alphas, and then it's going to look like a quadratic program, and then we can solve it. Okay. So right, okay, so now this is where we are. We're down to here, having used the stationarity conditions and plugging in the solutions. So now what we're going to do, actually we only plugged in 2 of them. So we're going to now use the first of the results I got from the stationary conditions, which was the gradient with respect to the weight vector is equal to 0, and that gave me this here, right? So now, from the last slide, I had this, and I'm going to just plug in W there, and I'm going to plug in W there, and so that's just going to give me this. Pretty straightforward, right? Nothing complicated. Just, again, plugging in the third solution to try to simplify it further. So now I've gotten rid of the betas, I've gotten rid of the W's, I've gotten rid of B, and I've gotten rid of epsilon. So actually this is now just the only parameter left here among all the primal and dual variables, I think, is alpha pi, right? The rest are just training data. Okay, so that's pretty good progress. And in fact, you can rearrange the terms here a little bit. I'm not going to bother to go through. It's just some algebra. There's nothing fancy or complicated. There's no tricks. And then you can, if you want, you can write it in this matrix form here, which again is a classic quadratic program. And so actually, you can see how it's not a lot of steps. Once you understand the formulation of the Lagrangian and how it's achieving the optimization problem you want, and you know these, I mean, you could go and look at how these KKT conditions are derived, but for this course, just assume them to be true, so we just make use of them to get expressions, substitute them in, and now we've reduced it to a quadratic program in the dual variable lambda, and we can now make a call to a quadratic program solver in this alpha variable. Is the logic clear? Okay. So just in summary, we went from here to here using a bunch of stuff from EE 127. Okay, so good. So now next we're going to do two things. One is we're going to try to understand some of the intuition of the constraints in the KKT, see if this gives us insight into what's going on in the problem. And the other thing we're going to do, and I think I should have switched the slides around, but I didn't, is we're going to actually say, well, given the alphas, how do I go get the actual classifier, right? Like, how do I get W, how do I get B, what does it look like? So, but first, let's get some intuition of what happened here with the math. So having found the optimum, after calling the quadratic programmer on that quadratic program on the dual variable alpha, we know that the KKT conditions are satisfied. And remember, this is a convex problem, and so there's just one global optimum here also. And so let's take a closer look at this. So one of the stationarity, there were three stationarity conditions which arose from the derivative equal to 0 for each of the primal variables. And I think this was the third one was this. Which we saw before, and there were two we haven't yet looked at, so we didn't yet make use of these, but they're going to be interesting for the intuition, and these are what we're called the complementary slackness variable, and the intuition of these is that it's for inequality constraints, and so alpha I and beta I are the dual variables for each of the two kinds of inequality constraints, and what this complementary slackness basically says is either that dual variable has to be 0, or that constraint has to be slammed up to exact equality. It was only an inequality constraint, but if it's equal, then this whole thing is 0. And so what complementary slackness is getting at, kind of intuitively, is like, is that constraint like been pushed to the edge or not? Right? If it's been pushed to the edge, then this thing is 0, and otherwise this thing is 0. So it lets us somehow get a sense of when things are being pushed to the edge. And similarly here, so either beta is 0 or the slack variables are 0. I mean, they could both be 0, but we're going to use some arguments now based on these complementary slackness to get some more insight. So I'm going to rewrite these three things just to keep them in mind, and this is where they came from, so now I'll put them just down here because we're going to make use of them. And so now there's weird underlining. I could not get off of PowerPoint. I don't know what happened, so just mostly ignore the underlining. Oh, so now we're going to, basically what we're going to try to do is understand what's going on when alphas, for different values of alpha. For alpha equal to 0 and things like this. And say, like, does that mean something that has some intuition according to the problem I've set up about the margin? So if alpha is equal to 0, then, do I have my ink? Oh, I had it inked up. I feel like this is the wrong slide deck somehow, but hopefully it turns into the right one. Okay, so if alpha is 0, I can make use of this condition here that tells me that C has to be equal to B, right? And if that's true, if C is equal to B, then beta I is non-zero because C is non-zero, which means that epsilon is 0, the slack variable. So I can use these two conditions here to conclude that the slack variable is 0. And what that means is that training data point, the I training point, didn't need any slack, so it's either on the correct side of the margin or it was on the margin. That's kind of cool, right? That you can get this out of the Lagrangian and the KKT. And why is it interesting? Because you may recall, and I'll show you again, but the weight vector was the sum over alpha I times the training points. And all the ones that are 0 don't go into the predictive model, because it's very sparse with respect to the training data. Only the support vectors dictate the margin, right? And so these are basically all the ones that don't affect the margin, because they're going to fall out of the weight vector. Okay, so now let's consider what happens if alpha is not equal to 0, and there's going to be two cases here. And one is when it's equal to C, and one is when it's not. So if alpha is not equal to 0, so that's here, then basically we know that that B, just rearranging these, B is equal to C minus alpha, and that this has to be greater than 0. greater than or equal to 0 because that's the constraint on the dual variable for inequality. It says beta has to be greater than or equal to 0. So, okay, so that's this. And now within that, there's a subcase. The subcase says, let's consider when alpha I is equal to c. So not only is it not 0, but it actually specifically has the value c. So in that case, then c minus c is 0, and beta is equal to 0. So we know over here now that beta is equal to 0. And so what that means is epsilon is basically free. It could be 0 or it could be non-zero. However, since we know that alpha was non-zero, because that's one of the assumptions we're in this clause, then we know that it does influence W. And so it has to either be on the margin or it has to violate the margin. And then finally, if alpha is not equal to 0 and it's not equal to c, then we know that it's somewhere between 0 and c. And if that's true, if alpha is between 0 and c, then how does this one work? Then beta is not equal, yeah, so then just from this, beta cannot be equal to 0, or that wouldn't be true, so that's from the second condition. And if beta is not equal to 0, then that means epsilon is equal to 0. And because epsilon is not equal to 0, I can take this third constraint here, and, because alpha is not equal to 0, I can divide out alpha from here, and I get that, basically I get that just this part has to be equal to 0, which means this thing is exactly true, and moreover, epsilon is equal to 0, so this means it lies exactly on the margin. This might be a little bit fast, so maybe I should have slowed down. I've already seen it, so I know it, the logic of it. But I think it's also explained reasonably well in the notes. But maybe just to give you a pictorial summary of this, is what this says is that the alpha variable, remember, I should have put the slides the other way, but alpha is the weight factor is the sum of every data points alpha I times the training data itself. And so if it's 0, it falls out. And so what this actually, the argument we just went through is that when alpha is 0, it's actually on the correct side of the margin, and so it shouldn't affect the margin, and so that's consistent with the intuition that it's not going to affect the value of W, which is defining the hyperplane. And meanwhile, if alpha is if alpha is between 0 and c, then we're on the margin, and if alpha is equal to c, we could be on the margin or outside the margin. On margin or violated. That's right. The picture here is violated. So the point here is, even if you didn't follow all the logic, the point is that I wrote down these conditions, which I know to be true from KKT. They were from the stationarity to the complementary slackness, and then from there I can make a series of arguments that basically tells me that the points that are support vectors are these ones here. And this one actually, because it violates the margin, right? So if it's on the wrong side of the margin, it's going to end up with a cost function, which will also affect it. Any questions on that? Yep. Right, not the center dividing line. I mean, the margin means this thing here. It's just, and you can see her here. So, for example, if you're, and actually that's a good point, is if alpha is equal to c, you could still be correctly classified in the sense that you're on the correct side of the decision boundary, but you might, but you've still violated the margin. You're not sort of outside the buffer zone. Yeah. And so even though technically you would get correctly classified, you affect the margin because you violated it. Any other questions? Okay. The epsilons are just a readout of how much you violated the margin, right? Like this here, basically these red lines are the epsilons. And actually, that brings me to the next slide, good segue. So actually at the optimum, the slack variables are as small as possible. And the reason they are is because we penalize them in the cost function. So if they weren't as small as possible, if for some reason it's bigger, you would just make it smaller and your cost function would be smaller. So what that means is that this inequality constraint is actually tight. So you actually get that epsilon is either, it's either 0, right, because it didn't violate the margin, or else it's 1 minus this. which just arises from rearranging the terms here at equality. And so we now know exactly the value of epsilon. And what's interesting about that is you can actually now rewrite the optimization problem, the very first one we wrote, before we wrote all the weird, crazy Lagrangian stuff, and you can just actually now plug this in for epsilon. So we remember this is the margin here, to maximize the margin, minimize the reciprocal margin, and this was to minimize the cost. It used to have an epsilon here, but now I've put this guy in, because I know it to be true at the optimum. It's just, again, plug and play from the realization that this becomes an equality. And when I do that, what is this? This is the hinge loss we saw last class, and this is essentially a ridge penalty. So you can see that, like, sometimes you start with models and intuitions in one direction, and they emerge from somewhere completely different, right? So ridge penalty also came out of like a Bayesian Gaussian prior, and now we see there's actually a connection between a ridge regression penalty and max margin. There's a very tight connection between these. And the other thing we see is that you might think of like hinge loss as this thing that's a surrogate to the 0-1 loss, which we can't use because it has no gradient. And so you might say, well, let's use this loss, let's use that loss. But you see here that also if you just set up an SVM with max margin and you allow slack variables, it actually emerges completely naturally from there. So it's almost, I think some of the most beautiful things in machine learning are the way you get to the same thing with completely different intuitions. It's pretty remarkable. So, and technically you can, like if I divide this, right, because it's not quite right, so there should be a lambda here for ridge, and this should be divided by the number of points. So I can just, if I divide here by, if I multiply this by 1 over NC, and then similarly here, then I actually get an explicit value for lambda. I didn't write it in there, but it would actually have like a completely direct mapping. It would basically be hinge loss regression with a ridge penalty, like exactly that. I didn't do the last step of dividing by n. And of course, we can multiply this by any scalar, and it's the same optimization problem, right? So it's just to change the interpretation. Okay, so that's it's really strange. Let me look, because I feel like there's slides that I wanted to go through. I see. I think I went through it in the soft SVM, and I didn't want to be repetitive. Did I? This is not this slide deck from last time. Let's see. I'll put it in there. Yeah, I did. Okay, this was the thing. Okay, I had this last time, so I didn't do it again for the soft margin, although we'll see something similar. Right, so once you have the alphas, then you get W by just computing the sum, because you know the alphas, and these are the training data points. And of course, the sum is sparse, because most of these things are not support vectors, and they have an alpha equal to 0. So the weight vector is given by the linear combination of just the support vectors. And to recover B, we have to use one of those conditions again, notably the complementary slackness condition. And we get one for the case where alpha I was not equal to 0, so we just pick one. Pick one of the cases where alpha I is not equal to 0, it's not a support vector, and from that we can just back out of the complementary slackness that this is true, and from there we just solve for B star. So you can do that with any single point. You can calculate B as long as it was not a support vector. And now the decision function is the same kind of decision function we've seen all over, which is W times X plus B. Or you can also, if you want to write it in its dual form, that can be kernelized because it has these inner products of X. Now it's just the alphas times YX plus B. Okay, so that's what I kept thinking was in this slide deck. And there's a version of it, but so before we get to that, was my laser pointer just working or not? It wasn't, right? It was. Oh, it was. Okay. I thought when I switched that, it doesn't work. Okay, so everything we've done now, we've gone through hard and soft and primal and dual, and I kept referring to that we can kernelize it. So now let's actually just like go through that a little bit more, even though you should have had already a very good introduction to kernelization from the first half of the class. And so we know that sometimes, like in this case, if you use this, what would be implicitly a linear kernel here, because it's just X transpose X, then you get a linear decision boundary. So even with all the fancy margin and the regularization, at the end of the day, we saw what it looks like, right? It's just a linear boundary. And so, of course, this is often not convenient. And so we can, as we saw much earlier, right, we can augment with polynomial features. So just basically expand out x. Or we can implicitly augment them using kernels. Right? And I say implicit because the idea with kernels is you replace the inner product of x transpose x with the kernel, and you never have to explicitly compute the features. That's sort of the beauty of it. You can be in an infinite dimensional space and just work in a finite kernel. Right, and so to use kernels, we had to kernelize ridge regression, which meant that getting it in terms of x transpose x. In that case, we didn't do it with Lagrangians. We did some math, and then it fell out. But this is often a more systematic way to do it. And right, and implicitly, these kernels correspond to an augmented feature space, but this is like a basis expansion here. And then you're taking the inner product. Only the beauty of kernelizing it is you replace all the explicit occurrences of x via this inner product with the inner product of the augmented space only with the kernel. So you never actually compute these things. It's just like conceptually you do. So, right, so now what does this look like? These are the slides I was looking for. So this is how we saw it in the whole development I just did. It was the original feature space. And in that case, it just looked like this. This is basically what we just derived. That looks different. So I mixed and matched some slide decks. So now I guess the difference. That's the quadratic program. Sorry. Okay, no, that's all good. Right. So basically, in the original feature space, this is what the decision function looks like. Exactly. It's just alpha I in the dual. I'm just writing the dual now. Alpha I times y times these inner products b, and right, potentials are 0. So now that's original feature space. And now I can think of this in some augmented feature space where I do explicitly compute these if I wanted to. And so in that case, I would just replace x with like some basis expansion of x up there and down here, and now the decision function would look the same as it did here, except instead of x transpose x, I just get these phi's, right? And then in the full kernel space, I just replace those phi's with the kernel, and now I have no explicit mention of x by itself, only kernel inner products of the x's. So again, I get this kernel, that's how the kernel version comes out. And I think you've seen this already. I always like this example, maybe because when I first learned kernels, I learned about it, but if you had, imagine you had two classes, one was like on the inside of a circle, the other on the outside of a circle, then if I use a basic quadratic kernel, then I go from a space, the original space in which there's not a single linear separating hyperplane, to a transform space in which there is, right? So in some sense, these kernel methods are always linear in the augmented space, the implicit augmented space, they're linear in them, but you don't ever even compute that, right? And so that's why one way to think about it is you're shifting the points around into some weird high dimensional space, and then you're putting the linear hyperplane down, which you can do more easily, hopefully. Okay, so there's a whole sort of kernel engineering thing. So there's many kinds of kernels, that's this slide. Right, like you've seen polynomial. I think you saw RBF. Something called like a class of min. There's all kinds of kernels. There's even kernels that are meant for graph-based data. So when like some people do their whole PhDs on devising kernels for particular problems. This is like more in the old days when SVMs were very hot. And then you can also take any kernels and compose them. So basically, kernel has to be positive definite. And so as long as all the operations you do maintain that, then you're good to go. Okay. Right, and there's a lot of technical details about kernels and Hilbert spaces and all this that is not in here. If you're interested, Jean-Philippe Verne, who's at Google and Paris, has been doing this stuff for years, and he has some nice slides. So, right, and then one other small note here, which is I have over and over said, okay, we've reduced this to a quadratic program, go call like a regular quadratic solver for these kinds of problems. This being the sort of final kernel SVM, soft margin. And so, but it turns out that in practice, people actually do use specialized solvers that can be more efficient. And so there's a famous one by John Platt, who actually I worked across the hall for years at Microsoft, called SMO, Sequential Minimal minimal optimization, and it's actually typically more efficient than the standard solvers out there. And I'm not going to go into the details, but it basically uses some heuristics that are very specific to SVMs in order to make a very SVM dedicated quadratic solver, if you will. And it requires some heuristics as well. And if you're interested, actually, Andrew Ng has some notes on there that give you a nice idea of what that's about. You're not responsible for it. So, right, so SVMs are not probabilistic, right? And that makes me cry because that just seems crazy. Because I guess a lot of what I do, we want probabilities because they have meaning. You're making decisions with them. You're averaging things, and I just really want one. And so this has been one of the big problems with these. And actually, John Platt, again, he's the one who actually solved this. I guess he must have been really interested in SVMs at some point. So normally the way you use an SVM is you just compute the sign of W times X plus B. But because we were working in this margin formulation, right, there was no probability model here. So there's no probabilistic interpretation. The only interpretations you get are kind of distance from the separating hyperplane. And so you could take the, so you could remove the sign will just give you 0, -1, or 1, right? If you're on the boundary 0, otherwise -1, 1. If you took the sign away, then you'd get some sort of score where if it's positive, it'd be indicative of some sort of distance to the one side, and if it's positive, it'd be indicative of a distance to the other side. So score tells you something, but you don't know like the scale of it, right? Because it's not a probability, it's like unbounded. And so the question is, can you do something to SVMs to get a probabilistic interpretation? Because in my mind, every model should be probabilistic, and John must have known this because he did this. And so you can do this thing where you basically do this post hoc training of the data. You train the SVM, and after you've trained it, you now basically build another model on top of it where the feature is the SVM score. So it's basically what's inside the sign here. That's going to be a feature, and you're going to pipe it through a sigmoid, which we know gives probabilities, and we know the class label, the actual 0, 1 class label. So now we're going to fit this model with maximum likelihood by tuning the parameters A and B with like gradient descent. And what that's, so it's like a second process on top of the SVM that gives now the SVM probabilistic meaning. And so right, just in summary, you would train the SVM as normal, and then you would apply it to a validation set to compute some distances. So you, I guess, can't use the data twice, actually. I don't know why, I'm not sure if that's true. I don't know why you have to split the data. It seems reasonable to me not to, but I'll have to think about that. And right, and in any case, you learn the parameters after the fact. So you're not changing the SVM, you're fitting a layer, if you will, on top of the SVM to the sigmoid. Okay, so that's, and there's, you know, you can, yeah, I guess that's a pretty thorough summary of SVMs. And so it's interesting because I asked people who have GSI'd for this class numerous times, what do you think the take-home message of SVMs are? And they said, I have no idea. Like if they got an, you know, A or A plus in the course. So I like in my mind, the sort of summary, the take-home points here are that, well, there's new way to regularize called max margin, and it has these really interesting connections to ridge penalty and also hinge loss. So basically, the ridge penalty kind of falls out of the max margin, and the hinge loss falls out of, well, I guess that's not the regularization, that falls out of the slack variables. So that's like a really interesting kind of profound intellectual insight. And so what it also means is we now have these two views of like small loss, large margin. There's some sort of, if you will, quote unquote, duality there. And then the other thing was just re-emphasizing the point, but one of the points often with SVMs, people sometimes learn about kernelization only with the SVMs, and then they later on learn about other stuff. You guys have already learned this. And sometimes SVMs, because they have a hinge loss, are said to be robust to outliers, and that's because the hinge loss basically on the bad side, as you violate the margin more and more, it only penalizes you linearly because that hinge loss is linear. But if you think about other losses like exponential loss and logistic loss, like these go up more steeply than that. So, you know, whether that's good or bad, you know, it's hard to say, but it could be more robust to outliers for this reason. The other thing is it's a convex quadratic programming problem. And so that's one thing that kernels sometimes let you do. And I guess it's sort of a sleight of hand because you don't know how to pick the kernel. But given that you've chosen a kernel, then you have a convex problem. So right, that's kind of like you do linear regression. And if you put in enough features, it'll be really powerful and it's still or logistic regression is still convex. Right, it's not probabilistic, but we can use this band-aid fix, the Platt scaling, to make it probabilistic. And if we're working with kernels, then we can only use the dual formulation, a thing that's written in terms of alpha I. And so you don't have a choice in that case, because you can only kernelize one of those two things, and it's the dual one. And so the dual ends up having to deal with these kernels. Is this actually, right, I think in the QP program it scales, I'm trying to think which part of it, it scales cubically in the number of data points, which is often horrendous, especially nowadays. And I guess that comes into the quadratic solver, which has this n by n matrix in it implicitly or explicitly. Okay, so sometimes after class, people say like, well, should I use this model? Should I use that model? And so I want to make a few comments on that. And so this is a paper that actually came out in this is the Journal of Machine Learning Research, a very well-respected and rigorous journal, and it was a year ago. And this is, we're not going to go into details here, but it's quite interesting that there are results coming out that say that you can induce regularization in your model by virtue of the optimization procedure you choose. And so in particular, what's emerging is if you use gradient descent on unregularized logistic regression, and if the data is separable, then what happens is they show that the predictor converges in the direction of the max margin. Basically, you end up with a max margin solver. So max margin kind of corresponds to ridge, and yet even if you don't add the ridge penalty to logistic regression, but you do gradient descent, you will end up with a max margin solution. So this is pretty mind-blowing, right? And then they have some restricted results on layers of deep neural networks that have the same thing. And they point out that because of this, you may want to keep training even if your training loss is 0, and in neural networks, you often try not to get training loss 0, but sometimes you do. And actually, we're gonna have a guest lecture by Anand Sahai, who's gonna tell us about some really interesting new results of his about that. But in any case, what they're saying as a consequence of this is with logistic regression, if you've already hit 0 training error, you may want to keep pursuing gradient descent because it actually has a regularizing effect because it's bringing you towards the max margin solution, although it's doing it really, really slowly. And then the other thing is that I think hasn't been in the course before is a good theorem to know. So we're not going to go into the technical details of it, but it's called the no free lunch theorem. Basically, what it says is that if a model is to be useful for something, it has to have some bias. Like the bias might be that I think it has a linear hyperplane in the original space. It might be the neural network has this architecture. The use of convolutions is a bias, right? Like every decision you make and how you set up your model is a bias of some kind because it restricts the representational capacity. And so, for example, even though a neural network is in theory a universal approximator, as soon as you pin down an architecture, that's no longer a universal approximator, right? You've pinned it down, and now it's like it has a sort of bounded capacity of what it can represent. And so any model that's useful has a bias because you can't have one that doesn't. Basically, it's kind of related to the bias variance trade-off. Like it would just have infinite variance, right? And so the no free lunch theorem says that any useful model has bias, and because it has bias, it cannot be universally the most useful. And so all this boils down to is if you have a real data problem, you cannot know that there's one best model out there, and you're going to have to go do some empirics like cross-validation and all these kinds of things. So now no one can ever ask me after class what the best model is for their problem. Okay, so, and then one last thing that I think often also doesn't get mentioned a lot is the notion of like, what are hyperparameters and how does the notion of hyperparameters affect our ability to do cross-validation? Does anyone know, does anyone have an idea of it? I actually didn't Google this. This is my definition I'm gonna write down. But does anyone have an idea of what a hyperparameter is? Or let me actually say this. Sometimes we have hyperparameters, and so what I mean by that is like the ridge regression parameter or the C parameter in the SVM. And we always say, let's fit these with cross-validation, right? And they can't be optimized with the loss function. So I don't know if you stop to think about it, but who can explain to me why these hyperparameters are hyperparameters? Like, why aren't they just regular parameters that we learn as part of the loss? Let me just give like everyone like 10 seconds to think, and then is it obvious? Like, who's just like, yeah, obviously. I don't think it's obvious, because I remember last time I taught this course, like half the staff were like, what? Okay, someone, yeah? Maybe. That's not the answer I have. Let me just say what it is in Ridge, you've added like a lambda times the penalty on the weight. And if you just did gradient descent on lambda to minimize the loss, you would just drive it to 0 and you turn off the regularizer. And the same thing would happen with C and SVM. So it's the way it's set up is like you just can't, because it will turn itself off. And that's why. And of course, the reason you want to have it on is to do with how the thing generalizes. You're in some sense preventing overfitting, and the only way you can really do that is to check for different settings how it works on like a holdout data set, and that's why we have to use cross-validation to fit it. So, okay, I'm glad I put that in. It's not obvious. Is it? It's not obvious. Who thinks it was obvious? Who thinks it's not obvious? Who understands it now that I've explained it? At least 20%. Okay. Does anyone have a question for those who didn't understand it?
Thinking like maybe like differentiating the hyperparameters wouldn't be meaningful. Is that valid?
Well, I mean, it depends what they are, but if they're real, like the lambda parameter is a real valued parameter, so there's no reason you couldn't take the derivative, follow the gradient, but it will take you to 0.
But yeah, like doing that optimization wouldn't be like meaningful.
Right, I mean, you could turn the crank of gradient descent, like you could just say, I declare it a parameter, I declare I will turn the crank of gradient descent, so you get nonsense out, because it's like, you can see what will happen if it will go to 0. Yeah, so usually when we talk about hyperparameters, we're referring to these other kinds of parameters that you cannot tune by minimizing the loss, because they actually take a hit on, they cause grief to the loss, and they want to get rid of it. Yeah. Okay, so in these cases, as we said, we use cross-validation. And now I want to make one other point, because this is another one that I've noticed a lot of people don't know. So normally, I have a quiz, but we're running out of time, so I won't quiz you, I'll just tell you. So normally we run, we have data and we split it into like you can do train test splits, or you can do cross-validation. In this case, it's like threefold cross-validation, right? You train test, train test, train test. But now, normally, well, we've been maybe, I don't know how it was taught exactly, but often this is taught in a little bit of a sloppy way when we're talking about how do we estimate the accuracy and the value of the hyperparameters. And this is a little bit nuanced if you haven't thought about it. And so the question is, can you use just regular cross-validation, as I've written here below, to do this? And so again, because we're running a bit short on time, I'm going to say, like, actually, no, you can't. And the reason you can't is you're going to, it's going to be a biased estimate. You're going to get an overly optimistic estimate of the accuracy, because you're basically using the same fold both to fit the hyperparameter, and so you get to pick the best one there. And so there's some sort of winner's curse. Like, you test many, many values of lambda and you pick the best one, then it's actually going to be an overestimate of the accuracy of the model. And so in these cases, you need to, if you're doing cross-validation, then you want to do something that we sometimes call nested cross-validation. That should be written here. And sometimes you'll refer, especially with deep learning now, deep learning is often so expensive they don't do cross-validation, they split stuff off, and then you'll just hear sometimes that there's a train, a test, and a validation. And that you can do these things in different ways. Then you don't have to do the exact procedure here, but you always need this notion of 3 different sets. And so essentially the validation set is to pick your hyperparameters. Once you pick them, only then, with the one best set, do you go test. And that's how you get an unbiased estimate of the accuracy. And the idea is that you basically cannot choose, you can't touch the label more than just when you're estimating the accuracy. So if you touch it also to estimate the hyperparameters, then you're inflating it. So this is not a rigorous technical argument, but this, if you sit and think about it, it's very clear. And actually, although I have to say, when I was, before I started grad school, I had an argument about this with a professor somewhere who didn't believe me, a machine learning professor. I don't quite understand how, and I actually implemented it and showed him, and he said, oh. So you can test this out, and you can see that you get an inflated estimate. Okay, so SVMs took a bit longer than I expected, but where we're supposed to go next is K-nearest neighbor, and we have half an hour, so actually I've never given a lecture on this, so I don't know how fast it will be, but let's give it a shot. Do you guys, is the stretching guy here? Do you want to stretch before we do it? Yeah? Okay, let's have like a 10, 20, 30-second stretch break. You could talk to your nearest neighbor. Well, nobody groaned. I'm impressed. All right, let's go to K nearest neighbors. Are you stretched in the back? All right. Okay, so I emphasized this point just now, which is that in SVMs, the decision rule was defined by an average over a few key training points, which were these support vectors, which either lie on the margin or violate the margin. So we always write it as over all the data points, even though we know most of them drop out to 0, right? So I could rewrite this over a very small sum of data points. Instead, just all of those that are support vectors. And then it looks like this. Okay, great. What does that get us? So it might make you wonder, like, is there some other way that I can find a rule of this kind that is to take an average of some small set of training points to make a decision? Right? This is just, at the end of the day, taking a few training points, and then I'm basically saying how close are they to my test point, and then averaging it based on the kernel distance and the supervised label, plus an offset term. Okay, so you could think maybe more generally that I'm going to define some set S, and I'm going to make a decision for point J by taking the label of all the points in S, indexed by I, and then computing some function, which is a function of the test point itself, plus all the xi's, and then labels. I guess I could have just put that in. So it's sort of just stepping back a bit from SVM and say, like, does it make sense to do this in some other way? And so, in a sense, this is what K-nearest neighbors is doing. And K-nearest neighbors is the simplest predictive model you will ever learn in your entire life. And you can write it. You don't even need to write pseudocode because you can just read K-nearest neighbors and you almost know who already knows what it is, but didn't know before, and inferred it from the title. Anyone? Who wants to make a guess? In the back? Not quite, not quite. All right, it's good I'm giving the lecture. It's gonna find, for each test point, it's gonna find the K closest points to itself, and then it's just gonna say, take a vote of their labels. So if most of them are a 1, then I'm a 1. If most of them are a -1, then I'm a -1. So they can just make a vote, or you can turn it into a probability. If I have 10 neighbors, and half of them are 1 and half are -1, then maybe I have a 50% decision, right? So, so what it's really doing is you find the K nearest neighbors and you just average their labels, and then you take the sign. That's what I just said, this is basically voting. Great, now who understands K nearest neighbors? Please, all of you. Maybe that's like an upper bound when you ask that question in a class. It's 50%. That's the max now of any question. No one can never be more than 50%. So right, and this contains the K nearest neighbors. And so implicitly I wrote this function before, but here it's really just 1, so I didn't write it there. But you could imagine that you may want generalizations of this where it's not. And I think we'll briefly mention these. And so, right, you're just taking the majority vote of your K nearest neighbors. It's like really, really simple. In fact, often machine learning courses, they explain this whole algorithm in the first 5 minutes of the first lecture. Although they don't go very deeply into it. Okay, so what is the actual algorithm? Basically, there's no training procedure at all. Like we just go straight to test time because there's no training. As long as you have the data, then you're good to go. The data are and the number k, that is the model. There's no other training. And so, so we go straight to test. So you calculate, you have some query point here, calculate the distance to every point, all these cute little things. And then from that, you choose the k closest ones, and then each point gets an equal vote. Okay, so I just said that. Now it's even more obvious. Who can code? Who thinks they can code this? Okay, pretty good, pretty good. And we can remove the sign to get a probabilistic interpretation. If I now consider y to be 0, 1 instead, then I just average these and I don't take the sign. Now I have a sort of probabilistic interpretation because it's between 0 and 1. That's a remnant of the past slide. That is not the average. Oh, it is, right. It is the average of the class level, yeah. And you can actually, we're not going to talk about it here, but you can use it also for regression. So imagine this is no longer a label 0, 1. It's actually like a real value regression label. You can do the same thing, and it will also work. Okay, so I sort of brought this up using SVMs and said, oh, this is like, let's step back, let's think about this more generally, and like, oh, let's do this KNN thing. So what are some of the key conceptual differences between these? So they look really similar, but if you stop and think, there's actually some key differences. Does anybody see one off the bat? It's like a major conceptual difference? Like other than the margin, like forget the margin, forget the loss function, forget the regularization, something else.
Choose which points are important.
Yes. What about it? What about it?
For SVMs, it's like the support vectors. Those specific points are always going to. Well, I guess maybe depending on what you're.
The support, no, you're exactly right. The support vectors are always the special set of points, no matter what your test point. So whatever test point you use, the support vectors are always the same. Once you train the SVM, the special set is fixed at test time. But with KNN, each test point has its own special set that you have to go find, right? So that's exactly right. And also in SVMs, you actually use a weighted average because this alpha, when it's 0, it falls out, but when it's not 0, it has like it can be any value between 0 and C, and depending if the higher it is, the more influence it has, right? And so that's another difference. But the really interesting thing I'd say is that the special set is changing at each time with KNN. So, and then also the SVM uses this very explicit kernel. And I kind of hid that right now. I just said, you say, oh, you just compute the distance. Well, okay, the distance implicitly can correspond to like kernel, or at least some, you have to choose a distance measure. Yep. No. In the basic version, not. I'll show at the very end of this slide deck. There are there's training that has to do with speeding. To speed it up, you use fast data structures on the training data. But conceptually, like if you don't care about implementation, then conceptually there's no training. And so, in fact, that's a good segue to the next slide, which is that, and that's a general truth of what we call non-parametric models. So I mentioned briefly this in another context, non-parametric tests in statistics and non-parametric models in machine learning. And basically, training means store my data and pick a parameter like k. But given that you've picked k, like if someone told you k, then like there is no training. And so the KNNs are the simplest possible non-parametric model. And essentially the parameters, if you will, are k and all of the training data. Like that's all you need on your hard drive. And so with non-parametric models, there's no training phase because test time involves just like a lookup into the statistics of the training points, such as the class of your k nearest neighbors. And so conventionally, one way people describe non-parametric models is that the size of the model grows with the size of the training data. That's because in some sense the model is the training data, right? Which sounds completely crazy, and it kind of is. Like who would devise a machine learning model where you just say like memorize all the data? But it turns out you do. And but in contrast, for parametric models, which is like a neural network and like logistic regression, all these other things, the number of parameters is independent of n, right? It's just like the dimensionality of the feature space or something like this. Well, a neural network, it could be huge, but it's not dependent on the number of samples. And so sometimes these are called instance-based learning or lazy learning. So instance-based, because basically the whole prediction is based on just the instances, like statistics of the instances. And it's lazy because you're not doing any training. You're just completely lazy and you leave all the effort to test time. And so also as a consequence of this, test time tends to be very expensive because you typically have to scan through the whole data set, and we'll get to that. So, so these sound crazy, and you might think, like, why are we learning these completely ridiculous models? Turns out they actually work well, and I have a cool slide at the end of one of these outperforming one of Google's big convolutional neural networks. So maybe that will make you pay attention. But just to give you an example, like one of the classic examples, and this is like the classic MNIST data set. So these are 1616 bitmaps, grade scale. They use a Euclidean distance. I said you have to pick a distance. So, but what that means basically is the pixel-wise, right? Euclidean distance between every pixel. And you can see here, if you use 7 nearest neighbors, you get a 95.2% accuracy. Some SVM, I don't know what kernel they used, but it's 95.8, a little bit better. And humans get 97. So basically, just by always looking at the 7 nearest neighbors, you get pretty close to human accuracy. So again, like that tells you something. And so in fact, some of my colleagues here, like Alexei Ifros, Alexei here, the office is across from mine, he does really cool work. He I don't know if he still uses them, I think so. This is from 10 years ago, and they have many papers out where they use these on really cool vision problems. And this particular one, it's something about finding the GPS coordinates or a country location of where a picture was taken. And they trained it on trained in quotes, right? They have 6 million training images. I don't know the exact version they used because we're going to talk about some ways to get it over the expense of scanning all the data points, which is problematic. In fact, that's like almost the main problem with them. Okay, so the point of the last slide, 2 slides, was like these things actually work. They're competitive with much more sophisticated models. They get used in real research. Even still, I know that was from 2008, but they incur this really large memory footprint, and they're computationally expensive. Large memory footprint because you cannot throw away any of the data if you take the sort of vanilla version. And they're computationally expensive because at test time, I got to scan through all the data points looking for the k-nearest neighbor for every test point. Whereas once I have those support vectors, I never find them again. And they also don't work well in high dimensions, although lots of stuff does work well, but these in particular work really badly. So we're going to look into some of these issues in more detail in a little bit. First, I want to go through some more of the basics. So, we've talked a lot about decision boundaries. So you might say, what does the decision boundary look like for these things? And usually people explain these when you use just one nearest neighbor, because then it's kind of really easy. You can think of a Voronoi tessellation. So take each of these are like training data points, and a Voronoi cell is basically everything inside the cell is closer to this point than to any other point. And similarly for this cell, and the boundaries of the cells are just these lines here, right? And all the Voronoi cells together are a Voronoi diagram. And so, so the KNN doesn't, and the 1NN doesn't explicitly compute a decision boundary, but we can use these sort of Voronoi diagrams to get a sense of what the decision boundary looks like. So you can do it very easily for one nearest neighbor, but even for higher ones, you can explicitly compute it and draw it, and I'll show you. What's going on? Ooh. Okay, so now I've taken those Voronoi tessellations and I've just colored them with a class. So this is like blue class, and this is red class. Okay, and so now what I can do is I can say that the decision boundaries arise anytime there's a mismatch at one of those edges in the color. So in this case, I have an example with 3 different classes, and I do a Voronoi tessellation, and then everywhere where there's a mismatch in color, that is the decision boundary for one nearest neighbor, right? Just by a definition. Like it literally comes from the definition of one nearest neighbor. And then now if I go to higher number of neighbors, I cannot use that exact same argument, but I can still compute them. And actually, I think there's some online tools where you can like drag. I was looking for a good one to show you guys, but it must be a good one. I didn't have time to find one where you can drag like number of points, number of this, number of that, and see how the decision boundary changes. But looking at this, do you see anything interesting that you haven't seen before in all our discussion of decision boundaries? I heard somebody said something. Someone over there said something. Yeah, what? Sorry? It's non-linear. Well, we've seen non-linear, like we've seen crazy, curvy things, right? If we, I guess non-linear is always a bit tricky because when we do linear regression or logistic regression, we get a linear decision boundary. If we augment the features, then we have linear in the augmented feature space, but not in the original space. But okay, but so yeah, I guess this is not linear in the original one, so that is true. Although if you use a kernel, it would be similarly true. So that's a good one. Is there another one? What do you mean by smooth? Yeah, I mean, you could get pretty crazy non-smooth boundaries, although you could probably get crazier ones with this, but you could probably do some really crazy stuff with kernels, and maybe we haven't seen them. Any other ideas? These blank spots are, I believe they are where you're 50-50. I'm not sure, but I was wondering that. But the point that I was going to say is there's completely discontinuous regions, right? Like I have purple here, totally disconnected from this purple, and I don't think we've seen that in this class before. Have we seen it? Did you see it somewhere in this class?
Did you not get that with
Mixture of Gaussians is unsupervised. It has no decision boundary, right? So remember decision boundary here. Yeah, so, but as you can imagine that k nearest neighbors is somehow like arbitrarily flexible. Like if you could imagine just designing data points to get kind of whatever decision boundary you wanted, right? And so that sense is very powerful, but usually this can also hurt you. And so analogously in 3 dimensions, one nearest neighbor, you would get these sort of 3D Voronoi tessellations. And so, and you can't make the Voronoi argument, but you can compute the decision boundary for different values of k. And so when k is 1, you get these kind of crazy boundaries, right? Because it's paying only attention to one point. So it's kind of like crazy high variance, if you will. And if I go to k15, I basically smooth it out, right? Because now instead of taking a vote from one thing near me, I'm taking a vote from 15 things. And so this has like a smoothing effect on the boundary. Does that make sense? Okay, so going back to one nearest neighbor, imagine that I have this noisy sample in the middle of the red cloud that has a blue point. What that means is everything in its Voronoi cell is going to get labeled blue. And if you look at this, you think, well, that's probably wrong, and so I'm going to make a lot of mistakes for like everything in here is going to be wrong. And so sometimes it's like very sensitive to outliers. And so by using k greater than 1, we would get to average across more points, and we'd be less sensitive. And in this particular example, if I use 3 nearest neighbors, now suddenly everything in this cell actually would get the correct classification. This sort of corresponds somehow to smoothing the boundary as well, right? These are related to each other. Okay, so that's good. So should we just take k out as large as we can computationally afford? What? Who can see a reason not to? Let's think, here's a thought experiment. Take k to be the number of data points. I guess -1 because you can't choose yourself. So think it through. What's going to happen? Everybody just take like 20 seconds to think what will happen to k nearest neighbors if I let it use always all the other data points. And then I do a vote. I do a hard vote. You're either 0 or you're 1 after the vote.
Should I? No.
Yeah?
Maybe like the points, class of those data points is going to dominate and all.
That's exactly right. So if you take k to the limit of the size of the training data, then the vote is the same for every single point. And the vote will just be the dominant class. So it's completely useless, right? It's only basically looking at the class distribution. So that's probably not generally desirable. So every point gets the same prediction. So from that, we know like that increasing k could possibly be useful. Probably k equal to 1, not always great, but then if we go too high, and so, right, so how are we gonna choose k? We're gonna do what we always do for hyperparameters. We're gonna use cross-validation, and usually there's some sort of sweet spot between 1 and like the maximum. And and I just described this, so I guess if these lectures had been decoupled more, then I would maybe ask you these, but it's just this point about hyperparameters. So right, so we use it, and we get the same kind of plots that you saw earlier in the course, where the training error goes down, 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 but the test error kind of plateaus, and then it goes back up, and so you want to pick it off where the test error or the validation error. Technically, this should be the validation error if you care about also estimating the accuracy. And there's this part here called, in purple, it's labeled the error rate, and in the legend it says Bayes, and we're going to actually find out what that means at some point in this slide deck, either today or next time. But it's basically, what this is a theoretical lower bound of what you can achieve. And as you see, the test error doesn't dip below it. The theoretical bound doesn't count for the training error, it's above the test error. Okay, so what happens if I keep k fixed, but I increase the number of training points? Who thinks that's a good idea? Like, should I take it as big as I can computationally afford? Yeah, I think that's a good idea. So, and intuitively it says that as n gets larger and larger, as I start sampling more and more, I basically have better coverage of the space, and the points that are near to me are going to be actually nearer as a consequence of that. And if they're nearer to me, then then they should somehow be more meaningful in averaging their votes. So we're probably getting better exemplars to vote, and the performance should improve. And so in general, adding data to any reasonable modeling approach should make it better. Sometimes it should never hurt unless you're adding from a different distribution. But if it's the distribution you care about and it's the same distribution, it should always not make it worse. And sometimes you see like a plateauing effect where there's like a diminishing returns and then like a no more returns. And somehow if you've gotten all the representative data, then it might not help you and it might just be more expensive. Okay, so I mentioned this sort of optimal error. It's called the Bayes error, and it's a general principle that's not related to KNN, but I just want to go through it as a general principle, and then I want to tell you, and so what it is some sort of optimal error, and what I'm going to show you is a theoretical result about how good KNN does to the best theoretical model according to this criterion of the Bayes error. And we won't go through the actual result, we'll just state it, but it's quite impressive. So far we've talked about methods to evaluate classifiers, and they've all been data dependent, right? Like we do cross-validation with the data, or we draw the ROC curve, or we have a precision recall curve. And so in each case, we have to train the classifier, and then we assess it on this test set. And so if we change either the training data or the test data, we'll change the number, which doesn't seem unreasonable, but you might imagine that we might want some sort of more fundamental property of a classifier that's more inherent to it and not about the data. And to do this, you generally make some assumptions, and this gets into sort of statistical learning theory, which is not in this class. And so this is maybe just like a hint of this kind of idea, but you could go, in principle, take a whole class about it. I'm not sure if there's one here or not. But, and so what we're going to talk about is the expected risk, where you're basically, in a sense, you're integrating out the data, so you're not dependent on it. And so I'm just going to give you like a very brief set of slides to give you this idea of what the expected risk is and how that relates to the Bayes error of a classifier and how it fits in to KNN. So the risk of a classifier, F, for the loss L, so that's just the predictive model, that's the label, is there's different kinds. So one is, well, the empirical risk is kind of what you're familiar with, is you just take your training data points and you compute it for each point and you average it. So this is what's called the empirical risk, fancy term for something you've seen a lot, and we can calculate it. The thing that we can't really typically calculate is what's called the expected risk. And this is the thing that's not dependent on the data, because we just kind of, if we knew the distribution, the joint distribution over X and Y, then we would just average out the loss of that classifier over all of them. And then it would be it wouldn't be dependent on them. So this is the sort of idea of expected risk. Right. So assume that we could compute this expected risk. We knew the joint on Y, and that we could train a classifier, in particular a probabilistic classifier, that would give you the probability of the target given the X. So even if we had the best perfect probabilistic model, like absolutely perfect, we still might not get zero risk. Like the expectation might not be zero. And why is that? It's kind of related to the curves you saw for the AUC. Remember I said AUC is some sort of like ability of the classifier to distinguish between the distributions. But like if the distributions overlap completely of the two classes, you can't build a classifier, right? Like there's nothing you could do, you just can't separate them. So to the extent that they are separated, if you can find features in a functional form, like a parametric or non-parametric model that lets you use them to tease the difference apart, then you're good to go. But there's some fundamental limit, which is that if the distributions like of the sort of scores of the classifier, if you will, don't separate, then you just cannot have a good classifier. So the more fundamental property. And so the best you could ever, it turns out, it's not obvious, but it turns out that the best you can ever do for a 0-1 loss for that expected risk is to just use the argmax from a probabilistic model. And so if you do that, then the expected risk of this sort of perfect procedure is called the Bayes risk or the Bayes error. And so it's somehow a property of what the best possible predictive model can do given how well those distributions of data are separated from each other. And so the reason I'm telling you this is, well, one, because you're taking an intro to ML class, you should have heard this term and have a rough idea of what it is. But the other reason is that this is one of the main theoretical results for k-nearest neighbors, which is that asymptotically, which is not always super useful, the number of data points, asymptotic the number of data points, the empirical risk of one nearest neighbor is at worst twice the Bayes risk. And so the Bayes risk is some sort of like optimal thing to do, and you're at worst, you're twice that. And so that's actually a pretty strong theoretical guarantee. And so there's actually less intuitive results that's just for one nearest neighbor. You can also, there's more for KNN, and if you're interested in stuff, you can take a look at this book. But so that's the point here is to say with these simple models, they seem to work well in practice. And now the point is there's also actually some theory that backs this, that says there's this notion of a theoretically optimal Bayes error rate, and this thing gets pretty close to it, like by a factor of 2. Okay, I think the next set of slides are, I don't want to start a new topic because there's like a minute left, so I'll finish this off next lecture. Thanks.